Welcome everybody to the Fields number 3 seminar. You just probably heard our my informal chat with our speaker today, Samit, about the state of the pandemic where he is. I hope wherever you're joining us from that you're safe and healthy, taking care of yourself, and of course doing math. Today, as I said, the speaker is Samit Dasgupta, who's from Duke, and he will speak about Stark's conjecture and Hilbert's 12th problem. Samit, please.
All right, thank you very much for the invitation to speak. Yeah, it's funny giving these online talks, and I hope to one day visit and come back to Toronto. So I want to speak on Stark's conjectures and Hilbert's 12th problem, which Mahesh, my collaborator, spoke on a related topic on, this is joint work we're doing together. So everything I'm speaking about today is joined with Mahesh. But I want to maybe highlight some different aspects. So I want to begin with a discussion of class field theory and the topic of explicit class field theory. So class field theory describes the Galois group of the maximal abelian extension of a number field F in terms of, say, the ideal class groups or the ideal class groups, depending on your perspective. So in terms of the ideal class groups, it's given by this formula. The Galois group of the maximal abelian extension of a number field F is given by a certain quotient of the ideal class group written here. And what's important here, and the reason that we view this as a solution to understanding the Galois group, the maximal abelian extension, is that the right side uses information that's intrinsic only to F itself. That is, somehow if you know F and everything about F, then you know the right side of the equation. So then we know something about something that doesn't isn't intrinsic to F, which is this maximal abelian extension. And I mean, this, of course, it's canonically attached to F, but it's somehow, you don't know how to construct it even if you know F, whereas you kind of know how to calculate the right side if all you know is F. So explicit field theory, class field theory, asks for exactly that, which is, can you construct the field F ab using only information intrinsic to F and not just the Galois group of F ab over F? So in the first case, we want to think about is F is Q, the field of rational numbers. Then class field theory tells us that the Galois group of the maximal abelian extension of Q over Q is isomorphic to Z hat if you work out that quotient of the ideal class group that I gave before, which you can think of as just the product of ZP stars. I don't know if I said Z hat, I should have said Z hat star. So this is isomorphic to the product of ZP stars as P ranges over all the prime numbers. And explicit class field theory goes beyond this and actually tells you what the field is. And so the field QAB, the maximal abelian extension of Q, this is a famous theorem of Kronecker and Weber, is the compositum of all the cyclotomic fields, or the union. It's equivalent if you view this as sitting inside the complex numbers. You take e to the 2 pi I over n, and you would join that to the field of rational numbers for all n, then you get a large field, which is the maximal abelian extension of Q. And the only other case where we sort of know an answer to this question of what is the maximal abelian extension of a number field F explicitly is for quadratic imaginary fields. So F is Q adjoint root negative D, where D is a positive integer, okay? And the theorem there is that Fn, so Fn here denotes the ray class field of conductor n, that it's given by adjoining the J invariant of an elliptic curve with complex multiplication by the ring of integers in F, together with essentially the coordinates of the n torsion points on that elliptic curve. So this Weber function is a little modification, which sort of makes it exactly right, but it's essentially the coordinates of the n torsion points. Okay, and I just want to say here that the role of this exponential function, e to the 2 pi ix, which showed up in the case of Q, is played now by these modular functions. Okay, so J is the classical modular function, the usual modular function in the upper half plane. And you can view these Weber functions of the n torsion points of the elliptic curve as special values of modular functions also. So in other words, modular functions evaluated at CM points are playing the role of the exponential function evaluated at rational points. So the exponential function being e to the 2 pi ix, evaluate that at rational points, and that gives you the maximal abelian extension of Q. The modular functions play the same role, evaluate at CM points for these quadratic imaginary fields. And I just want to point out that these are the two cases where we kind of say that explicit class field theory is classically known. Of course, what's classical is always a question, but people usually say that. And one thing that unites these two settings is that these are the number fields that have finite unit group. So that's something to keep in mind. And Hilbert's 12th problem which was stated in 1900 at his famed ICM address, it basically asks to solve this for arbitrary number fields. So I'll just read this. The theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. So that's the Kronecker-WEBER theorem that I mentioned at the outset for ground field Q. Then, since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So at the time of his writing, the theorem that I wrote on the previous slide about quadratic imaginary fields was not entirely 100% sort of, done and wrapped up with a bow. It was pretty much known, I think, that we could do something like this, but this theorem that I presented in that form was not known precisely, that you could get the maximum abelian extension of a quadratic imaginary field by these particular functions. But already at that time, Hilbert realized, okay, that's pretty much going to be done eventually. And what's really interesting is finally the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers or of the imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. So what I want to discuss now is approaches to this problem, Hilbert's 12th problem of explicit class field theory, using L functions, in particular Stark's approach. So Stark stated a series of conjectures proposing the existence of elements in abelian extensions of a ground field F, which I'll call H throughout this talk, whose absolute values are related to L functions. Stated these conjectures more and more precise throughout the 1970s. Okay, Tate made Stark's conjectures more precise, and he stated the so-called Brumer-Stark conjecture. So if you saw my introductory talk, I talked about Brumer's conjectures, which he stated informally in the 1960s, which were very similar in a flavor to Stark, which is proposing the existence of certain P units whose valuations are related to L functions. Tate realized that Brumer's conjecture and Stark's conjecture, where really this can be stated uniformly, where you either choose a finite place for Brumer's conjecture or an Archimedean place for Stark's conjecture. And so he stated this unified conjecture, and called sort of the case of the finite prime, the Brumer-Stark conjecture. So Gross refined the Brumer-Stark conjecture using p-adic L functions in a conjecture called the Gross-Stark conjecture, which I won't state precisely today. And lots of partial work has been done on the Brumer-Stark conjecture and the Gross-Stark conjecture, notably by Rubin, who made the higher rank version of Stark's conjectures precise, and Burns, Popescu, and Greither, who made partial progress on these conjecture, building, of course, on the deep work of Wiles on the USL main conjecture. So most results that we had known up to this point were based on the USL main conjecture that was proven by Mazur-Wiles over Q, but by Wiles over totally real fields. Okay, so let me just speak in qualitative terms now about what the Brumer-Stark conjecture and Gross-Stark conjectures are about. So we start with a totally real number field. So that's always our setting. So the ground field F that'll take us totally real. So the simplest case would be a real quadratic field. So Q adjoin root D, where D is positive. And you let H be a finite CM abelian extension of F. And the Brumer-Stark conjecture then predicts the existence of certain elements U, which are called Brumer-Stark units and that are related to L functions in this very specific way. And I'll tell you what that way is shortly. And the Gross-Stark conjecture then refines this conjecture by predicting that these units are related to p-adic L functions in a very specific way by a precise formula. So let me discuss some of my prior work in this area before the results I want to mention today. So in my PhD thesis, which I did under the guidance of Ken Ribet and Henri Darmon, who was informally my advisor at McGill, I stated an exact formula conjecturally for Brumer-Stark units. And then this was developed later in further joint works with Pierre Charrois, Matthew Greenberg, and Michael Spiess to handle the case of arbitrary totally real fields. So my thesis was just in the case of real quadratic fields and inert primes, and the general case was stated over a series of works over several years. At the same time, I was also working on the Gross-Stark conjecture, which was stated by Gross and in 1980-ish, I think. And eventually we gave a complete proof for the conjecture, again, in a series of works. So the first paper was joined with Darmon and Pollock. Kevin Ventullo, who was a grad student shortly after the writing of this paper with Darmon and Pollock, became interested and removed some of the conditions in our theorem. And then together with Kevin and Mahesh Kakde, we proved the full rank version. So my work with Darmon and Pollock was initially just in the rank 1 setting. Now I have an asterisk here on this slide when I say prove the Gross-Stark conjecture, because part of the Gross-Stark conjecture is the non-vanishing of a certain regulator. And we didn't prove that, but we proved the other aspects of the conjecture. So the non-vanishing of the regulator is kind of a statement in transcendence theory that's very similar in flavor to Leopold's conjecture. So somehow the general result conjectures on non-vanishing of regulators give you both Leopold and the non-vanishing of this regulator, which is called the gross regulator. So they're very much a similar flavor. And it's a very different kind of statement than what we actually prove, which is proving that that regulator is equal to a leading term of the p-adic L function without showing that it's actually non-zero. So when we say leading term, we should say expected leading term. Okay, so the new results that I want to speak about today are a proof of the Brumer-Stark conjecture as long as we invert 2. So there's always this annoyance at p equals 2, which we are thinking about, by the way, but it's just very, very initial thoughts on how we might handle p equals 2. It's very thorny at p equals 2. But so for, if you tensor the conjecture with z bracket 1/2, or alternatively tensor it with zp for any odd prime p, then we have the conjecture. Again, I know I haven't stated the conjecture yet, but I wanted to give you the results first, and then I'll state things precisely afterwards. And the second theorem is that my conjectural exact formula for the Brumer-Stark units holds. And again, there's a little bit of an error. There's a bounded root of unity. Okay. And I just want to say that I claim that this gives a p-adic solution to Hilbert's 12th problem for totally real fields, because Hilbert's 12th problem is asking for the construction of the field f(ab) using analytic functions depending only on f. You can show that the Brumer-Stark units, together with other explicit and easy to describe elements, generate this maximum abelian extension. And the exact formula expresses the Brumer-Stark units as p-adic integrals of analytic functions depending only on f. So it's something you can compute intrinsic to f. And I'll give examples of this at the end of the talk. So therefore, the proof of this conjecture can be viewed as a p-adic solution to Hilbert's 12th problem for these totally real field ground fields f. Okay, so now let me start to state things more precisely. So let's begin with Stark's conjecture in general. So H over F is a finite abelian extension of number fields. So right here on this slide, there's no condition on what type of field F has to be. And I write G for the Galois group of H over F, but I assume that G is abelian. So that's what I mean when I say that H over F is a finite abelian extension. I just mean that G, that's Galois, and that its Galois group G is abelian. I let V be a place of F that splits completely in H. So this can be an Archimedean place or a finite prime. If it's Archimedean, that means that V is real and the places above it in H are real, or it means that V is complex, and of course then it automatically splits completely. The place above it in H are necessarily complex then. And S is any set of places of F containing the infinite places, the ramified places, and V. And I denote by E the number of roots of unity in the upstairs field. So I discussed this E a little bit in my preparatory talk. So under this notation, Stark's conjecture states that there exists an element of H star which is a unit away from V. That is, its absolute value is 1 for every place of H that does not lie above V. Okay, so the only place where it doesn't have absolute value 1 could be at places above V. And at the places above V, these are indexed by the conjugates of any one fixed place W. So what's going on here, it doesn't say, but I fixed one place W above V. And then all the places above V are then the conjugates of W, the sigma W for sigma in the Galois group. Then I'm going to tell you the absolute value of U at all those sigma W's, and I'll express it by saying that if I take the linear combination of the logarithms of those absolute values given by chi of sigmas, chi goes over all characters of the group G, then I get the derivative of the associated L function. Okay, so this is a sort of a deep conjecture that connects something analytic, a derivative of an L function, to something algebraic, that is the valuations of a unit. So furthermore, there's this extracute aspect of this unit, or this V unit U, which is that its E through generates an abelian extension of F, which Stark found computationally, and I discussed this condition in my preparatory lecture. So a technical remark is that for this formula, this is sort of the fine print for the experts, that for this formulation, we must assume that the set S has size at least 3, I think. Okay, but I just want to mention that if you want to make a connection, what is the connection to Stark's conjecture? Which is that formula, as I said, it gives you this linear combination, but you can solve those linear equations and get the absolute value of U. So when I say under each embedding H into C, this is under the assumption that V is an Archimedean place. So if V is real or V is complex, then this absolute value of U that showed up in the formula is the absolute value of U under every embedding of H into C or R. So the question is, can you find this and propose the formula for U itself? So if the place is real, then and you know its absolute value, then you pretty much know U up to a sign. So that's not a big issue. But the question is, if U is complex, can you give a formula for U? Knowing just its absolute value is not really enough. So that's a little bit of a gap between Stark's conjecture and Hilbert's 12th problem, which is that if we had an analytic formula for U, then that would say intrinsic to F, I would be able to produce analytically an element of the complex numbers, which is I call U, which generates actually this Galois extension of F, this abelian extension. And that would give me a way of constructing canonical non-trivial elements of these extensions. And you could try to hope then that all of them together generate the maximum abelian extension. So that's the gap. We don't know a precise formula, except, so that's, when I say we don't know from Stark's conjecture, but there's been work since Stark's conjecture, and there are interesting conjectures in this direction to give an exact formula for U initially by Wren and Czech, and then in a certain different situation by Charrois and Darmon. So these are all in the case where this place V that I started with is a complex place, and your U lives in the complex numbers, and you want to give an exact formula for it rather than just its absolute value. And that's what these conjectures by these authors provides. Now let me go away from the Archimedean conjecture and speak specifically about the Brumer-Stark conjecture, which is the non-Archimedean conjecture. So for this, we fix a finite prime P, and this is the prime that's going to play an important role. There's also an auxiliary prime Q, which plays a somewhat less important role, but it's there to make the statements precise. And then, so P is playing the role of my prime V in the previous slide, my place V. And the place above it, which I call W, I'm now calling Gothic capital P, which is the prime of H that lives above this P. So you just choose one, okay? One place above lowercase Gothic P, this capital Gothic P. And I let S now be all the infinite places and all the ramified places in this extension H over F. Then the conjecture of of Brumer and Stark, which was actually stated by Tate in this combined way, is that there exists a U, which is a P unit that again has absolute value 1 at every place that's not above P. So saying that it's a P unit means it has absolute value 1 at every finite place that's not above P. And so I just need to say that it has absolute value 1 at each complex place, at each embedding of my field in the complex numbers. And then the valuations of the unit, or the conjugates of the unit at this fixed place capital P that I've picked, again, I take the linear combination and I get the L function. So it's not a derivative of an L function yet, because I've changed my notation slightly, that I've taken away the place P itself from the set S. And when you do that, that kind of divides by an Euler factor, which gets rid of the 0. And so you can state it more cleanly as an equality of these algebraic numbers. There's no logarithms and there's no derivatives. So this is a cleaner way of stating the conjecture. And if you unwind this, that is, you solve back for these ORD P of sigma views, then it's a theorem of Siegel and Klingen that the ORD P of sigma views expressed in this formula is a rational number, right? That if you solve these and see what you get on the left side, if I undo the linear combination and I solve for the ORD P of sigma views, then you get a rational number. But it's a deeper theorem of Deligne and Ribet and Kesu-Nogues that that's actually an integer, okay? And to get that integrality is exactly why I need to introduce this prime Q, okay? So it's this Euler factor here, this Euler-like factor. It's not exactly an Euler factor of the L function, but that it's which we call a smoothing factor, which makes it integral. So then this is a well-formed statement. That is, if you solve back for the ORD P of sigma views under this equation, then at least what you get is a collection of integers. They're integers related to something analytic, that is special values of L functions. Okay, and then the extra aspect of this conjecture with the insertion of this prime Gothic PQ is that U is supposed to be congruent to 1 modulo all primes of H that lie above Q, which is expressed this way. And what Tate showed is that this condition of being congruent to 1 mod Q is equivalent to Stark's condition that U to the 1 over E generates an abelian extension. Okay. Okay, so now I just want to show some pictures of the individuals involved in this in the statement of this conjecture. So STICKELBERGER, whose theorem I spent most of my preparatory lecture discussing, is the case of this conjecture proven over Q. Of course, he didn't have the general conjecture, he was just studying the case over Q. And in that case, we have an explicit formula for these U's. They're just Gauss sums. And he was able to prove the conjecture in this way. And Brumer wanted to generalize STICKELBERGER's setting to real quadratic fields and more general totally real fields. And he put forth a slightly modified version of the conjecture that I just stated. Stark, as I mentioned earlier, gave this conjecture for the Archimedean setting. And then Tate realized that Brumer's conjecture and Stark's conjectures could be unified. And he introduced this smoothing prime Q. Okay, so my theorem joined with Mahesh is that there exists an element U, so not quite in this P unit group, but in this P unit group, if you tensor with 1/2, that satisfies the conditions of the Brumer-Stark conjecture. I should also mention, even though I won't have time to discuss it today, that there's a higher rank version of the Brumer-Stark conjecture, where instead of 1' splitting completely, you consider R' splitting completely. And that's due to Carl Rubin, and we obtained this result as well after tensoring with C bracket 1/2. So the theorem that I mentioned earlier of Deligne, Ribet, and Kesu-Nogues is that there is a unique element in the integral group ring that interpolates all these L functions. So this is exactly sort of what I said about the fact that if you solve those equations back for what ORD P of sigma of U is supposed to be for all sigma, then you'll get a collection of integers. That's exactly saying that there's an integral element in the group ring, in the integral group in Z bracket G, that when you apply each character, you get exactly the left side of that equation that I stated before. And now I want to restate the Brumer-Stark conjecture in terms of class groups. So I haven't mentioned class groups at all today. So I want to define a slightly modified class group. It's the usual class group, but it's modified at the smoothing primes Q. So it's just the group of fractional ideals of H, as usual, modulo principal ideals. But instead of taking all principal ideals, you only take principal ideals generated by elements that are 1 modulo Q. And that's the sort of, it's a Q ray class group. And I denote that by class sub Q. And this is a G module. It's a module for the Galois group, right? You can always conjugate any ideal and get another ideal. So that gives you, and that conjugation preserves the principal ideals. So this is a G module, and the Brumer-Stark conjecture then can be stated more simply just by saying that theta annihilates this class group. If you think about what that means, the action of the Galois group is just sort of conjugating these ideals around. It's telling you that if you hit the ideal Gothic P by theta, and that you get an ideal U, then that U is the Stark unit. So if I start with my Gothic P, sorry, I might have said beta, the Gothic P, and you hit it by theta, and you say, okay, it annihilates in the class group, that means it's generated by some principal element, which I call U, then this U is exactly that unit showing up. This is the P unit in the conjecture. So this is what the Brumer-Stark conjecture is saying. And for this, it suffices to prove that, I mean, I make a big deal of this in the paper. This is slightly wrong, that there's a little issue at 2. Because remember, we had the extra assumption that the absolute value of U is 1 at every complex place, and there's a slight issue at 2. Whereas, I mean, if you could show that oops, I lost the presentation. Sorry. If you could show that theta over 2 annihilated class group, then it would imply the exact statement that I gave earlier. So there's a slight issue at 2, but in my talk, I'm removing everything, I'm ignoring everything at 2, so we can just ignore that. Okay. So now for this theorem, it suffices to prove this annihilation statement prime by prime. Okay, so you can tensor with ZP, and then it suffices to prove that it's the annihilator over ZP when you tensor the module as ZP, okay, for all primes P. And so we can kind of handle all odd primes. P equals 2 is a little bit difficult. And there's a refinement to this due to KURIHARA that I actually want to state, which is very beautiful, which is that theta should actually lie in the fitting ideal of not the class group, but the dual of the class group. So this is the Pontryagin dual. So this is the Homs into Q mod Z. Okay. And so this again, this minus side means we're projecting to the side on which complex conjugation acts by -1. And for that to work nicely, it's nice to make sure that 2 is inverted. So this is one reason already. So in the statement of this conjecture, we're assuming that P is odd. Okay. So minus side, there's no real ambiguity what you mean. You just sort of mod out or take the subset. It's the same thing. And the reason, so I understand that most people probably haven't worked with fitting ideals before, so I'm not going to spend too much time on this. But I just want to say that the fitting ideal is some ideal you can associate to a finally presented module over a ring, over a commutative ring. And it's always contained in the annihilator. So the fact that theta, if it lies in the fitting ideal, then it definitely lies in the annihilator. And then the annihilator of a finite module and its Pontryagin dual are the same. So that gives us the Brumer-Stark conjecture. So this is a stronger version that was proposed. And I actually want to state something, I don't think I've stated this before in a talk, so this is new, which is that there are conjectures of KURIHARA and Burns that refine that even stronger. So KURIHARA asked the natural question, well, okay, well, they both asked this question, which is, if I go back, remember the KURIHARA's conjecture was that theta is contained in the fitting ideal, the Pontryagin dual. There's 2 natural questions you can ask. One, what is the fitting ideal, the Pontryagin dual? Not just the theta is in it, what's the whole thing? And the second question is, change the other side. That is theta the fitting ideal of some natural module. And we have conjectural, answers to both those questions, and we've proven both of those conjectures also. So the exact fitting ideal of the Pointryagin dual of theta, of the class group, is given by not the theta that I defined before, but the primitive theta where you don't remove Euler factors at S, and then you include some other sort of factor for each ramified prime, okay? And then that's Kurihara's conjecture. So this is some generalized STICKELBERGER, ideal of STICKELBERGER elements. If you multiply through theta S infinity by each of these elements, you get generalized STICKELBERGER elements. So STICKELBERGER elements for certain subfields of the extension. So you're taking sort of STICKELBERGER elements for certain subfields. And you take all those together, that gives you the fitting ideal of the dual of the class group. And I'll just mention that theta S is what you get when you multiply theta S infinity by all of these Euler factors. If you multiply these together for all V and S ram, so this is just the set of ramified primes. If you multiply these Euler factors together times this, then you get exactly the theta that I gave in the previous slide. So that's the same theta here. And then I won't discuss the definition of the Selmer group, but there's a generalization of the class group. So the idea here is, as we all know, the class number formula says that the leading term of L at S equals 0 should be the class number times a regulator, right? So if the L function doesn't just see the class group, it sees something that should be like a regulator. So the Selmer group is some nice way of combining a regulator and a class group in an algebraic way. The regulator is some transcendental thing, but there's an algebraic way to view just the unit groups and the class group together in one module, which is the Selmer group. It's a very beautiful construction. And Burns's conjecture is that thing that combines the class group and the unit group should be theta. Now I should mention we're working on the minus side, so the units go away here, but there's still some sort of shadow of them, which allows you to see that you get the precise theta S here. Okay. All right, so we proved these. So I should mention that this theorem is in our paper. That's already posted on our webpage. But this theorem, we kind of realized only very recently how to prove it, and it will have to appear in future work. So now for the rest of the talk, I want to talk about how we prove these results. So I want to speak more generally first about RIBETS methods. So this is a diagram and philosophy that I've taken from Barry Macer, who gave a very beautiful talk at the 60th birthday conference of Ken Ribet in 2008. And he wrote an accompanying paper for the bulletin of the AMS, and a version of this diagram is there. So the question is, we want to go from from L functions to class groups. That is, we have the STICKELBERGER element theta, and we want to show that it annihilates a class group. So we need some connection between the L function and the class group. So how do we do that? This analytic thing on the left and this algebraic thing on the right. And we can't go directly across this dotted arrow. We have to make a big loop. So we first just make a connection between L functions and Eisenstein series. So L functions show up as the constant terms of Eisenstein series. This is something that's been known for a long time. So Siegel exploited this in his proof of the rationality of L values that I mentioned earlier. Now, Eisenstein series are certain modular forms. And of course, you can manipulate Eisenstein series to make CUSP forms. So every time, so the very first CUSP form anyone's seen, the delta function, right? How do you define it? Well, you take basically the Eisenstein series, the smallest weight Eisenstein series you can, so E4 and E6, and you try to take a linear combination of them where the CUSP term vanishes. So first you have to put them in the same weight so that you can start taking linear combinations and have something that makes sense. So you put them into weight 12, because that's the LCM of 4 and 6. And so you take E4 cubed and E6 squared, and you take whatever linear combination of them kills the constant term at the cusp, and that's basically delta. So basically, a fancy version of that is really what we do and what one does in Ribet's method is you take linear combinations of products of Eisenstein series, you cancel their constant terms, and you make CUSP forms out of them. Okay, and why do we want CUSP forms? Well, CUSP forms have Galois representations associated to them. irreducible Galois representations. Okay, and so now we've gone from left side to right side. Now we've made the bridge from something sort of analytic. You can define, you know, modular forms, Eisenstein series, in analytic ways as sort of infinite sums that converge. And then, you know, these deep theorems, you know, from the work of Deligne and Deligne-Serre, and sort of, you know, packaged together periodically due to Hida and Wiles and others. So there's deep theorems that there's Galois representations associated to these CUSP forms, which come from algebraic geometry at their source. So this is where the leap has been made from something purely analytic in some sense to something algebraic. And now with the Galois representations, if the Galois representations are irreducible but residually reducible, then associated to this, then from those Galois representations, you can extract some Galois cohomology classes. And then by Kummer theory, we can make a connection between Galois cohomology classes and class groups. They're Galois cohomological interpretations of the class group. Okay, so this is how we make the connection between L functions and class groups. This is sort of just a conceptual slide. Now let me be more precise. So what kind of modular forms am I actually working with? I'm working with what I call group ring modular forms. So these were introduced in some form originally by Wiles in his proof of the main conjecture. So what we do is actually a little bit even simpler than what shows up in Wiles, because we don't need p-adic families. We just need actual just finite collections of modular forms. So a group ring modular form is just a Hilbert modular form over a totally real field of a certain weight k, classical. This is a classical parallel weight k, whose Fourier coefficients lie in this group ring. Okay, so basically you just take the usual collection of modular forms with Fourier coefficients in Z, and you just tensor that with the group ring. But it has to have a certain nice property, which is that if you apply any character of the group ring, you then get a form of that Nebel-typus chi. Okay, so that's a compatibility. So this is really just a collection of forms of Nebel type chi for all possible Nebel types, but they have to be congruent in a certain way that the Fourier coefficients package together and give you an integral group ring element. So the fact that this is a ZP instead of QP is of central importance in this definition. If it was QP, then this would not be saying much. It would just be a collection of, you know, n independent forms of Nebel type chi, and they wouldn't have to satisfy any connection to one another. The fact that their coefficients packaged together into an integral grouping element means that those forms must have satisfied some congruences. Okay, and as for regular modular forms, it's very hard to just write down a modular form, right? So the modular forms that we can write down that are group ring modular forms are Eisenstein series. So I want to talk about the weight one, parallel weight one modular Eisenstein series, which I'm calling E1 of G, which is, and the reason that it's connected to our work is that the STICKELBERGER element theta is the constant term. Okay, so the constant term is theta divided by 2 to the d. D is the degree of my totally real field F. And it's the usual formula. So the mth Fourier coefficient is just the sum of the elements of G associated to to the divisors of that M. So this is a little bit of abusive notation. What does Q to the M mean if M is an ideal of O? Well, those ideals index the Fourier coefficients of a Hilbert modular form. So that I'm just saying the Hilbert modular form whose M Fourier coefficient is this sum. So I just write it this way to be familiar with respect to the usual notation over Q. Okay, and I should mention in level 1, this is slightly off because the constant term is different. Excuse me. Okay, but now from these Eisenstein series, I want to make a CUSP form. So how do I do that? Okay, so I want to take a linear combination. This is like what we did for delta, but a little bit more complicated. So I want to take a linear combination of E1 with some other modular form. So if I could make a modular form H, whose constant term was 1, then I could take E1 minus theta over 2 to the d times H, and that would kill the constant term, and I would get a cusp, something that was cuspidal at infinity. The problem is we don't know how to make a modular form with constant term 1, a group ring modular form with constant term 1 in weight 1. So we have to move to some higher weight, okay? So this is a theorem that you can produce a group ring modular form with constant term 1 at infinity, okay, as long as you're on a high enough weight. So that's hk plus 1. Okay, but now that I've made this weight k plus 1, I better make this form weight k plus 1. So I need to multiply E1 by a form of weight k. And that's what I'm calling Vk. And I want Vk to have constant term 1 also. But the point is that you want this CUSP form to be congruent to E1 modulo theta, right? So modulo theta, this goes away. And so you get E1 times V. So if you want this to be congruent to E1, you want a CUSP form congruent to an Eisenstein series, then you better get Vk congruent to 1. Okay, and it turns out you can do that. So this is two kind of deep results, which is that you can make modular forms, group ring valued modular forms, Vk and Hk plus 1, that both have constant term 1. Where Vk, so Vk is not a group ring modular form. Sorry if I said that. Vk is just a fixed form in fixed weight k and trivial Nevin type, right? If you multiply it by something that's a group ring form, then the product is still a group ring form. But Vk has to be congruent to 1 mod a very high power of p. Any high power of p that's large enough that theta divides it. Okay, and so then if theta divides p to the n, and v is congruent to 1 mod p to the n, that means v is congruent to 1 mod theta. And so this form is then congruent to E1 mod theta. Okay, so the fact that these Vk and Hk exist, so versions of these theorems were proved by Hida and Chai in slightly different contexts when they were dealing with lambdatic forms rather than these group ring forms. And the generalization to this context, which is slightly deeper, but basically, goes along the same route, but requires some extra work, was proven by my postdoc Jesse Silliman using some analysis of the minimal and toroidal compactifications of the Hilbert modular variety. So this is work of Silliman, which is very close to being released. The paper is written, and our work relies on it. Okay, and now once you get a form via this linear combination that's cuspidal at infinity, that is, we've killed off the constant term at infinity, you can modify it a little bit to yield an honest to goodness CUSP form that still satisfies the congruence that you want, that it's congruent to this E1 of G. Now you have a CUSP form. We look at the Galois representation associated to F. So now, of course, I just constructed F as a CUSP form. I didn't say it was an eigenform. So for simplicity in this talk, I'm going to assume it's an eigenform, but you can modify the argument to work if it's not an eigenform. In general, it won't be. But let's assume F is an eigenform. Then we know it has a Galois representation associated to it, which I call rho. And this Galois representation, now the thing is, we don't know that the Galois representation lives in GL2 ZP bracket G, and that's actually important and creates a lot of difficulties. We just know that the Galois representation lives in QP bracket G, because how do we make this Galois representation? We take the Galois representation of each of the separate forms individually, and we just take the product representation. But as I mentioned earlier, QP bracket G breaks up into a product over the different characters of basically QP, if the characters are QP valued. But ZP bracket G doesn't break up into such a product. So so this is why we only get something that's valued in QP bracket G. Anyways, but it turns out you can show that if you choose an appropriate basis, so in a basis for which the matrix of complex conjugation is diagonal, then you can show that the A and the D coefficients actually do live in ZP bracket G, and that A is congruent to 1 mod theta and D is congruent to sort of the group ring-like element sigma. So there's a canonical character, right, which from G into the group ring of G, which takes sort of an element to its group-like element in the group ring, and D is congruent to that character. All right, and that's because our CUSP form was congruent to E1 mod theta, and at a prime L, the Fourier coefficient, or the L eigenvalue, of Frobenius et al. Is 1 plus sigma L. And so that's what, so the trace of this matrix is then 1 plus sigma L. And you can use that together with the fact that you've chosen this basis in which complex conjugation is diagonal to give you that A is the 1 and D is the sigma. So I've taken complex conjugation to be 1, 0, 0, minus 1. And then that gives you that D is the sigma and A is the 1. Now, how are we going to make a Galois cohomology class? We've almost gone through this loop. We have Eisenstein series, CUSP forms, Galois representations. And so next I need to make a cohomology class. So that cohomology class is basically going to be given by the B of sigma. So where is the cohomology class going to be valued? It's going to be valued in the ZP bracket G module generated by this B of sigma. So this is some ZP bracket G module sitting inside QP bracket G. So you might call it a fractional ideal. Okay, so this equation, right, this is just from the group representation equation, right? B of sigma tau, this is just how you multiply matrices. B of sigma tau is A of sigma, B of tau was B of sigma, D of tau. That's just saying that rho f of sigma tau is equal to rho f of sigma times rho f of tau, and looking at the upper right-hand entry, which you get in that equation. Okay, and if I then reduce in, B mod theta B, okay, so B is a ZP bracket G module, so I can think of B mod theta B, that's a ZP bracket G mod theta module. Well, A is congruent to 1 mod theta, and D is congruent to, D of tau is congruent to tau mod theta, so I get, so this equation simplifies to as a congruence. B of sigma tau is congruent to B of tau plus tau B of sigma. And that looks very much like a cocycle condition, right? If I just multiply by sigma tau inverse, that whole congruence, then I see that kappa of sigma being sigma inverse B of sigma, that is a cocycle representing a class in H1 of GF valued in B mod theta B. Thurthermore, this class has some nice local properties. It's unramified outside the level and P, since those are the properties of the Galois representation. They're unramified outside the level, and P is the p-adic Galois representation. Now the problem, one of the big, deep problems in this theory of RIBETS' method is that this kappa is in general not unramified at P, right? So it's a p-adic representation, right? The determinant of the Galois representation associated to a modular form, the p-adic representation is a power of the cyclotomic character, which is ramified. So it can't, the representation can't be ramified because the determinant's not even unramified. So kappa is going to be ramified. To deal with this in the proof of the Iwasawa main conjecture, Wiles invented the so-called horizontal Iwasawa theory, which gained much fame because it turned into the Taylor-Wiles method, which was used to complete the proof of Fermat's last theorem. So this is a very deep and well-known process that has had many applications in algebraic number theory. But what we actually want to talk about today is a different way of getting around this problem of being unramified at P that is not using the Taylor-Wiles method. So the problem, I mean, we'd love to use the Taylor-Wiles method, but there are certain error terms that show up when you introduce these auxiliary primes that show up in the Taylor-Wiles method. And it seems insurmountable to get around that somehow, I don't really think you can, in this delicate kind of group ring situation where you can't have any error terms, you have to be precise. I don't see how to use the Taylor-Wiles method, at least I couldn't figure it out. So we had to actually deal with ramification at P head on. I should mention that people have tried to do this or sort of see what you could do with these auxiliary primes, and there's partial work on Brumer-Stark and certain very, very special cases where you can get what you want with this method. Okay, so Greither has a great paper on that. So let me, for now, not talk about that, and I want to sort of end the talk by talking about how we get around ramification at P. So let's pretend for now that the Galois representation is unramified at P, and let me finish the proof. Then the splitting field of kappa is then an extension, so it's unramified at all primes, so therefore the splitting field is therefore a quotient of the Hilbert class field. Okay, or I guess I said it's unramified. There still be ramification at the level, which could be this, these smoothing primes Q. So there would be some tame ramification there. So you actually get a homomorphism from this Q smooth class group. Okay. Now I didn't mention what a fitting ideal is, but fitting ideals have the property that if you have a surjection of fitting ideals, then the fitting ideal of the source is contained in the fitting ideal of the target. Okay. And another general property of fitting ideals is that if I have a faithful module B, then the fitting ideal of B mod theta B is contained in theta. Okay, because B is a faithful ZP bracket G module just by its definition. So then we get that the fitting ideal of the class group is contained in the fitting ideal of theta. Okay. And right, so this is all, I should have mentioned this, it says on the slide, but I didn't say it. This is all in the case when HORF is unramified. So that's why the only ramification you have to worry about is that these smoothing primes Q. There's no actual ramification coming from H being ramified. Okay, and I'll just mention that this inclusion, okay, is the reverse inclusion of what the Brumer-Stark conjecture says. If you remember, the Brumer-Stark conjecture said that theta annihilates something, and I said there's a strong version that said theta is in the fitting ideal of something. This is the reverse inclusion. Okay, so that's kind of startling. But in this case, when HORF is unramified, you can show that this inclusion is actually an equality once you have an inclusion, which is that these two ideals have the same size in a certain precise sense. Essentially that the size of the ring modulo this ideal is equal to the size of the ring modulo this ideal. So if one is contained in the other, then they have to be equal. And the way that you get the same size, right? This has to do with L functions. This has to do with class groups. That comes from an analytic argument from the class number formula, which tells you that this and this have the same size. So in a sense, you can think of this Brumer-Stark conjecture as a refinement of the class number formula. It's saying that these two objects that have the same size by the class number formula are actually equal as ideals to this complicated ring, the group ring. Okay. In the general case, let's see, do I say this? Yes. In the general case, when the extension is not unramified, then the class group, as I said, the fitting ideal is not generated by just theta. So how do you deal with, this reversing this inclusion to get inequality? So first of all, you don't get an inclusion in that direction. You get, you have to replace the class group from that previous slide with something more general, which is this Seller module or Burns in KURIHARA and Sano, which I mentioned earlier. And the Seller module replaces the class group, and that Seller module happens to have a surjective map to the class group dual, which is why the dual of the class group shows up. Okay. Okay. Now for the rest of the talk, I want to talk about, just have a few minutes left. I just want to talk about our method of actually getting a class unramified at P. So when I've completed the proof there, I assume that the class is unramified at P, but it's not true actually. So what do you actually need to do? So this is our new procedure that we invented to sort of get around the Taylor-Wiles method, or to sort of replace the Taylor-Wiles method because we couldn't get that to work. Which is that, okay, so it turns out that there's a higher congruence than just F being congruent to E1 modulo theta. It turns out that there is a certain non-zero divisor, which I call X in the group ring, such that there's a higher congruence between F and E1. So it's congruent modulo X theta, okay? And what is X? What X is showing, it's some shadow of the trivial zeros at P. That is, if chi is a character and psi of P is equal to 1, then the L function, L of chi 0, where P is in your set S, so LS of chi 0, where P is in S, that vanishes because there's a trivial 0 at P, because there's an Euler factor that you remove, 1 minus chi of P, and that's equal to 0 if chi of P is 1. Moreover, if chi of P is just congruent to 1, not equal to 1, but congruent to 1, then that Euler factor, 1 minus chi of P, is congruent to 0. So that gives you something that's sort of in the maximal ideal p-adically. And so sort of the accumulation of those p-adic factors is what this X is, okay? So it's giving you a higher congruence by these elements of the maximal ideal generated by 1 minus chi of P. And it's some integral way of realizing that there are these shadows of zeros, these mod p shadows of zeros. So I just want to mention that in order to construct the CUSP form F that satisfies this, it's a complicated procedure, and it involves not just looking at the cusp at infinity, as I mentioned in this talk, but looking at all the cusps. And if you look at all the cusps and give a very detailed and precise construction of the CUSP form, then you can see that you get these higher congruences. So I'll just say that the reason I mention is that traditionally in this RIBETS method, one deals with just this cusp infinity and then does some trick once it's cuspal infinity to get a cuspal overall. But we say, in fact, avoid those tricks and just calculate the constant terms at every cusp and see what Eisenstein series you need to cancel all the coefficients at all cusps, then you actually produce a higher congruence. Okay, the second step, okay, so now we have, instead of B mod theta, we have B mod X theta. Okay. Now the second step is you want a class that's unramified at P, right? So just mod out by inertia at P. Then your class is unramified at P. So you mod out by the image of your cohomology class, okay, which is basically just the B of sigma, it's just scaled by some units. So you mod out by B of theta for all sigma in the inertia groups. Okay, now the image of your class is tautologically unramified at P. Okay, it's almost silly. And so now that it's unramified at P, it's unramified everywhere. So for example, in the unramified, when H over F is unramified, then going back to our argument, now we have, just as before, instead of a surjection from the Q class group to B, we have it to B bar, where we've just tautologically made it unramified at P. And then because it's surjection, properties of fitting ideal show that the fitting ideal of the class group is then contained in the fitting ideal of B bar. And then the final step, which is a miracle, which is we can show via an explicit calculation of the fitting ideal that what you lose by modding out by inertia is exactly this factor X. So this X, which analytically showed up as giving us extra zeros of L functions, is actually an algebraic thing, right? It's just 1 minus chi of P. And algebraically, on the algebraic side, you see that it exactly gives you this extra factor. So what you get is that the fitting ideal of B times X is contained in the fitting ideal of B mod X theta, which by the faithfulness of BA, is contained in X theta. So now you can cancel the X's because X was a non-zero divisor, and you get the fitting ideal of B B bar is contained in theta. And since the fitting ideal of the class group is contained in that, we get the inclusion as we wanted before. So that's the modification of the proof. And I think that this should have more applications to block-Kato type conjectures. Okay, so I have one more minute, and I wanted to finish by just talking about my exact formula. So let me just sort of zoom through these slides, which is that the form of the conjecture is a p-adic integral. Let me just say that. So I have a conjecture for the exact, now I know these units exist by the theorem that I just described with Mahesh. What are they? So you can write them down p-adically, and this is a measure that only uses information intrinsic to F. It's called the Eisenstein cocycle. And you can actually compute these units. So let me just give one example for Q join root 305. The narrow Hilbert class field with the prime P equals 3 is degree 4. And you write down these 4 p-adic integrals and you take the elementary symmetric polynomials and you get these very nice elements of F. So you compute this to 100 p-adic digits and you get these very small numbers. And you check afterwards that the splitting ideal, the splitting field of that polynomial is exactly the narrow Hilbert class field. And here's another example with Q equals root 473, a degree 6 extension. Okay, and so let me just conclude by saying we can prove that F-ab is generated by all these U's together with some square roots where, so n minus 1 square roots where n is the degree of F over Q. Okay, so there's some simple square roots that you write down together with all these Stark units gives you F-ab. So now that we have proven that the U's exist and that we've proven the p-adic formula for them, you can actually compute the maximal abelian extension of any totally real number field via these formulas. let me just mention finally how we prove that conjectural formula. So this is work we're still writing up. Some new features are an integral version of the Gross-Stark conjecture due to Gross and Popescu and its relationship to the p-adic integral formula. And here we do use the Taylor-Wiles method of introducing auxiliary primes. Okay, so this is kind of gets rid of some unit ambiguity that shows up in the Gross-Stark conjecture. We get rid of it using the Taylor-Wiles method. All right, thank you very much.
Thank you. So you have to imagine everybody's applauding. You can't see it, but
yeah, well, I see some virtual applause on the
so
screen.
quite an impressive talk, a real tour de force, really beautiful stuff, Samit. Thank you very much for sharing that with us. We're almost out of time, though, unfortunately. If somebody, I don't see hands up, so I will take my privilege as the moderator to ask a question.
Sure.
So there are a couple of things. I mean, so the point is now you've got something stronger than what you initially wanted. Rather than an annihilator, you've got it sitting inside the fitting idea. That
Exactly.
must have other implications, no? That stronger.
Yeah. So one thing we showed is that the fitting ideal statement implies the higher rank Rubin's conjecture, right? So that's that was somewhat known, but kind of only a dual version of that appeared in the literature. So so we included the proof in our paper. But yeah, we get the higher rank Rubin's conjecture also, but only tensored with z bracket 1/2. So again, all these issues, you know, getting it to work at over z rather than z bracket 1/2 is something we've just like last week started thinking about. So it becomes very complicated. There's factors of 2 that show up everywhere, and there's actually a deep reason. It's not just technical. P = 2. Maybe I'll mention the thing about that, which is that when you, and this is something that shows up in RIBETS method and Bloch-Kato type things, when you have small primes relative to the dimensions, because we're working on GL2, and so that's related. That 2 is related to P = 2. And as you know, the theory of pseudo representations becomes difficult for small primes relative to the dimension of the representation. That's really where P = 2 becomes difficult. You want to rigidify your representation to make a cohomology class. So I say you take this basis on which complex conjugation looks at 1, 0, 0, -1. To get that A is congruent to 1 and D is congruent to sigma, you want to divide by 2. Because you basically, what you really get is that 2A is congruent to 2 and 2D is congruent to 2 sigma, and then you divide by 2. And you can't do that when 2 is not invertible. And then you lose more than just a factor of 2. The whole argument falls apart because you're using fitting ideals. And if you look at sort of B mod, if you take a module and multiply by 2, you don't just lose a factor in the fitting ideal. If the module is a product of 17 Z mod 2Zs, and you multiply by 2, you've lost a factor of 2 to the 17th in the fitting ideal. So this little minor factor of 2 completely kills the entire argument. So you have to do something that's really new in the theory of pseudo representations, which we are still in the process of thinking about.
Wonderful, wonderful. The fitting ideals played such a critical role in the original Maser-Wiles work too.
Absolutely, right? And it's a similar thing. Yeah, you wanna. It's basically you want to deduce certain things about modules from quotients, and deducing it from and basically want to deduce things from quotients, as you saw in my work. And annihilators don't work well. They don't behave well with respect to base change. That's the basic problem. Annihilator of a base change module is not just the base change of the annihilator, but that is true for fitting ideals. So the fact that the annihilator is the fitting ideal is contained in the annihilator makes it useful to work with the fitting ideal rather than the annihilator. Now the fitting ideal is not equal to the annihilator, so you can't prove something is in the fitting ideal if it doesn't actually live there. So you have to make sure that you have precise statements that are actually correct and that you're dealing with things that actually do lie in the fitting ideal. So you actually it's one of those things where you have to prove something stronger in order to get what you want, because the stronger thing has nicer functorial properties.
And you're just lucky that the stronger thing is true.
Yeah, I mean, we wouldn't have been brave enough to attempt this if there wasn't so much algebraic groundwork laid down since Maser, Wiles, and Wiles, like by Burns and Kurihara and Sano and Greither and Popescu. There's a lot of work that had been done, prior to, like these Selmer groups, these conjectures of Kurihara. We wouldn't have imagine that this would have had a chance of working if we didn't have that algebraic framework. So it was very useful for us. And some of this work is rather recent. So even though a lot of these techniques do go back, 40 years, some of the stuff is pretty cutting edge, the stuff of Burns, Kurihara, and Sano, and Greither, and Popescu. So it's a mix. Yeah.
Well, I mean, yeah. So I mean, your work itself is pretty impressive and very cutting edge.
Oh, okay.
Really beautiful.
Thank you. But yeah, we're definitely combining the work of very of other people. So it's there's a lot of background that goes into it.
Good. Okay, so I'm going to ask everyone to thank Samit again for a wonderful talk. And since we're out of time, I'm going to have to end the session now. Thanks again, Samit, and hopefully we'll be able to welcome you in person to the Fields Institute in the near future.
Thank you very much.
Thanks. Bye.